Hello dear students, welcome to Pen and Paper Chemistry on YouTube. What are we starting next? We are going to go on to haloarenes. We have already discussed the alkyl halides or the aliphatic halides. In this set of videos, we are going to talk about haloarenes or the aromatic halide derivatives. So before we go ahead with the topic, please don't forget your pen and paper. That's the reason the channel is named as Pen and Paper Chemistry, to remind you that you need a pen and notebook so that you can take down notes for future reference. Haloarenes or aryl halides, how are they different from the aliphatic halides? Aliphatic halides, what happens over here is the hydrogen is replaced by an alkyl group by a halogen atom in the chain. When we talk about the haloarenes or the aromatic halides, there the substitution takes place in the rings. You see over here? Here, the hydrogen of the benzene ring has been replaced by a halogen. If on the other hand, you've got an alkyl group attached to the benzene ring and we replace the halogen atom of that alkyl group. Now this is something similar to what we studied under aliphatic halides, right? So you have to understand the difference between the two. So it's a ring substitution, this is a side chain substitution. This particular set of compounds where substitution has taken place in the ring will show electrophilic substitution and nucleophilic substitution reactions only under extreme conditions. Whereas here, because of the side chain substitution, it will normally show you all the reactions, the nucleophilic substitution reactions of aliphatic compounds. Plus, of course, the electrophilic substitution which will take place in the benzene ring, right? So, you have to be careful especially when you are doing conversions, what is required of you. In today's video, we shall be talking about the preparation of haloarenes. There are two methods of preparation that we will be talking about. First is from benzene or alkyl derivatives of benzene by the method known as halogenation, and the second is from diazonium compounds. Let's start with the first one. When we say from benzene or alkyl benzenes by halogenation. So benzene, first of all, this is a ring compound, an aromatic compound. What do I mean by saying alkyl benzene? That means I have a ring and one of the hydrogen atoms is replaced by an alkyl group. But the substitution, further halogenation has to take place in the ring, right? So this is what we are going to prepare. When we say halogenation, halogenation means replacement by a halogen, right? We have spoken about this earlier under hydrocarbons, right? So let's write it down first. And what are halogens? Fluorine, chlorine, bromine and iodine, right? Now, if you recall, when we did the halogenation of alkanes, what is the reaction condition? Can you remember? Yes, we did it in the presence of light and it was a chain reaction. If you are not confident about this or you have doubts on this reaction, then there's a separate set of videos on the channel where the alkyl halides have been discussed separately. Now, under what conditions do benzene and alkyl benzenes undergo halogenation? Is it easy or difficult? Let's have a look. So, of course, fluorination, as we already know, it's an explosive reaction. So, no risk taking, we are not talking about it. Yes, it's an explosive reaction, so we don't carry it out also in the laboratory. Come to the second one. Chlorine and bromine, we know that they are like, brother, sister, they are going to behave similarly. So, whatever are the reactions with chlorine will be the reactions with bromine. Now, here the reaction can easily take place even in the absence of light. So, it's a very quick reaction even in the dark conditions, the temperature is low, but you need certain Lewis acids as catalyst. Can you tell me why do we need? If you notice over here, this is a reaction which involves substitution in the ring. So, the mechanism of these reactions is electrophilic substitution reaction. So, when it's an electrophilic substitution reaction, you need something to help the benzene get rid of its hydrogen and be substituted by an electrophile, right? So, that is why we need these carriers, we need these halogen carriers which will take the chlorine or the bromine to benzene and will say, this is a good person, you can make friends with it and let the hydrogen go away. So, that's how it works. Electrophilic substitution, does it make you confused, or are you nervous about this name itself? Are you hearing it for the first time? Don't worry, I have put a separate special video dedicated only to electrophilic substitution on the channel, which will make your fundamentals very, very clear. So, don't forget to watch the playlist on organic reaction mechanisms. So, would you like to complete the reaction over here? Yes. So, what do we have here? The hydrogen atom of the benzene ring gets replaced by chlorine. No, it's not a chain reaction as it was in the case of alkanes. If you want a chain reaction, the conditions have to be changed, right? Go on. Now try writing the bromination. So, if I say the reaction, the replacement is taking place by chlorine, the reaction is chlorination, right? What about when you are replacing by bromine? The reaction is bromination. The conditions of both the reactions, as I said, they are like twins. So, the condition for this reaction also remain the same. I have left it as a blank. Fill it, write the conditions. You can copy it from the previous one, but write it yourself. It will help you to gain confidence in the topic, and it will also help you to recall when you need it. So, what are we going to form over here? Yes, replacement of the hydrogen by bromine. So, the first product that we formed was chlorobenzene. What would be the name of the second product here? Write it. What will be the side product? It's not going to be HCl. What is it going to be? You notice over here the hydrogen from here taken up by the bromine, and we will have HBr, right? Let's talk about another variation of this. So, I have got an alkyl benzene. So, the alkyl benzene that I have taken over here is commonly known as toluene. What if I carry out this reaction under the same conditions? Now, I am leaving it as a blank. Pause the video, write the conditions that we did just now. Try recalling. Go ahead. Yes, it's dark. Correct. Low temperature. Perfect. We've got Lewis acids as catalyst. Very good. So, what are those Lewis acids? Iron filings, FeCl3, iodine. Very good. Good going. Now what will happen is, because of the presence of this alkyl group, now this alkyl group is ortho-para directing group. Oh my God, so many new terms. How are you going to remember? Don't worry, there's another video. I have compiled them under a separate playlist, and once you go through that playlist, I'm telling you, you'll find organic chemistry a lovely subject. So the replacement of the hydrogen by the halogen, and we will have two products over here, CH3Cl. Can you try? Would you like to try and name these products? So you see over here, yes, both of them are at the ortho position. So ortho-chlorotoluene. Would you like to give its IUPAC name as well? Go ahead, give it a try. And the second product is known as para-chlorotoluene, and both of these products differ a lot in their boiling point. So we are able to separate them easily. Because this methyl group has made the halogen atom go to the ortho and the para position, that is why we called it as the ortho-para directing group. Now you understand why we said that we can prepare aromatic halides from alkyl benzenes as well, but you have to see what you want to prepare. Okay, so we out of the halogens, we've spoken about fluorine, correct. We've spoken about chlorine, yes. We've spoken about bromine, yes. What is left now? Iodine. Now try recalling what we did about iodine. We said that when iodine reacts with alkanes, can you remember something special about this reaction? Think a little while, pause the video, think. Yes, anyway, I'll give you the answer, but it would do you good to think the answer. Very correct. It's a reversible reaction, right? So what do we do in order to get rid of this reversibility? We want the reaction to go in the forward direction only. What do? Yes, we need to remove one of the products. And what is that? Is it that we are going to remove? We are going to remove HI. How do we remove it? By using oxidizing agents which will convert it to water and iodine. And what are those oxidizing agents? Do you remember? What? Don't expect me to give you all the answers. I also expect you to have remembered what we've done in the previous videos, right? That's how we learn. We are moving ahead. So let's apply the same logic and let's write down the next reaction. So here also iodination is a reversible reaction, and again we are going to use oxidizing agents in order to get rid of HI, and those oxidizing agents can be, yes, HiO3, iodic acid, we can have mercuric oxide, we can have concentrated HNO3. All of these being oxidizing agents will convert the HI into water and iodine, right? So would you like to complete the reactions yourself first before I give you the answers? Then please pause the video and try them. Would you like to tally your answers? And remember, as well as notice that I have not balanced these equations, so you can balance them. So hydrogen iodide gets out of the way. Now see how you're going to write the reaction. I have not put any oxidizing agents above this arrow, correct? So I will show it as a reversible reaction. On the other hand, if I want to show that the reaction proceeds to completion, what will I do is, I will put it as a single headed arrow, but above the arrow I will mark over here oxidizing agents, and I can give the examples: iodic acid, mercuric oxide, concentrated HNO3. I hope this makes the point clear. Let's go ahead. The next preparation is from Diazonium salts. That's another set of interesting compound, which is a very good synthetic agent, in the sense that you can prepare a large number of aromatic compounds from benzene diazonium chloride. Just like you can prepare a large number of aliphatic compounds from Grignard's reagent, so you can consider them equivalent to the Grignard's reagent of the aliphatic compounds. I am not saying that they are the same, but we are drawing a parallel. Just like from Grignard's reagent you can prepare a large number of aliphatic compounds, so can you prepare aromatic compounds from benzene diazonium chloride. Now, this reaction was actually a chance discovery by a scientist by the name of Sandman. That is why we call this reaction as Sandman reaction. Initially, it was just the halogenation reactions here, that is treatment with CuCl or CuBr, which were classified as that. But now, generally, the conversion of benzene diazonium chloride to chlorobenzene, bromobenzene, iodobenzene, cyanobenzene is termed as Sandman reaction. See, it is easy. What do we have over here? Benzene diazonium chloride. Now, diazo is this group, N triple bond N, which is attached to the aromatic ring. Benzene diazonium chloride on treatment with cuprous chloride and HCl gives you chlorobenzene. Cuprous bromide and HBr gives you bromobenzene, and mind you, it is this Cl attached to the copper which replaces the diazo group. This diazo group is actually a very good leaving group. It leaves the benzene ring very easily. So, if I want to remove a group, I will convert it into a diazo group. Treated with cuprous bromide HBr, we get bromobenzene. With potassium iodide, actually you don't have to do much. You just shake benzene diazonium chloride with potassium iodide, and there you go, you have iodobenzene. Now, in your laboratory, you won't find benzene diazonium chloride in any of the bottles. Why is it so? Because it is generated in the reaction mixture itself when we need it. How do we prepare it? We've got aniline and we treat it with nitrous acid. Now, this reaction takes place under ice cold conditions. When you carry out this reaction in the laboratory, your teacher will provide you with ice separately in order to place in the dish so that you can cool your test tube while carrying out this reaction, right? So, this gives us the product C6H5N2 positive Cl negative. It's called benzene diazonium chloride plus, of course, water. Now, again an interesting thing. In the laboratory, you will not find any bottle saying nitrous acid. It's an unstable acid. So, how do I solve that problem now? There's a solution to it as well. Just like we prepared benzene diazonium chloride in the solution, we are going to prepare the nitrous acid also in the solution. So instead of taking nitrous acid, what do I do is, I've got this aniline, and in the reaction mixture, I'll take sodium nitrite and concentrated HCl. Again 0 to 5 degrees Celsius, and we have the same product C6H5N2 positive Cl negative. The purpose of taking this sodium nitrite and HCl, see again they are going to generate nitrous acid in the solution itself. Split it. Positive, negative, negative, positive. Yes, let's go back to the basics. NaCl plus HNO2. Isn't it easy? Right? So here of course you will get NaCl also as one of the products, and of course water. Doesn't it sound simple? So effectively in this reaction, if you notice, what have we done? We have converted aniline to a number of products. We've converted it into chlorobenzene C6H5Cl. We have converted it into bromobenzene C6H5Br. We have converted it into iodobenzene C6H5I. And how did we do that? We first converted the aniline into benzene diazonium chloride C6H5N2 positive Cl negative. And then this benzene diazonium chloride is treated with cuprous chloride NaCl, cuprous bromide NHBr, and potassium iodide, right? Let me write it a bit more neatly. Yes, and we shake it with potassium iodide. This set of reactions is termed as Sandman reaction. Now, if you want to be very, very specific, it is actually the conversion of the diazonium salt to these is the Sandman reaction. But in general, you will also find at places conversion of aniline to any of these clubbed under Sandman reaction. So that's why I just wanted to clarify this point to you. Now what about fluorobenzene? I want to prepare fluorobenzene. Is there no way that I can do it? There is a way. So what we did was we modified the Sandman reaction. So would you like to know about it? Let's get going. So again, tell me, how are you going to convert aniline into benzene diazonium chloride C6H5N2 positive Cl negative? Close your eyes and tell me. Now, this benzene diazonium chloride further on, don't forget to write the conditions over here. We've done this reaction just now. It's very, very essential to write it as 0 to 5 degrees Celsius. That's ice cold temperature, right? Benzene diazonium chloride is then reacted with the tetrafluoroborate ions. So we can use fluoroboric acid over here, positive, negative. What do we get? Yes, so we get the chloride ion replaced by the tetrafluoroborate ion. So we'll have C6H5N2 positive, BF4 negative, right? So it's benzene diazonium tetrafluoroborate. Now this product that we've got is insoluble in the reaction mixture. It is separated, it is then heated, and we get here C6H5F, again BF3, and of course nitrogen, as we said, is a very good leaving group, and it is happy to be on its own and it is liberated out. Interesting, right? How the Sandman reaction has been put to a good advantage to convert aniline into fluorobenzene, which otherwise directly would have been difficult. So this reaction is given a specific name which is known as the Benzene reaction. Right? I would like to stress over here that you can add or delete reactions as per your course curriculum. So supposing in your curriculum they have not mentioned about this reaction, please feel free to ignore it and go on preparing the chart based on the reactions which are there in your syllabus. So which chart am I talking about over here? Wouldn't you like to put all these reactions on one page so that you can have a quick glance through? There you go. So we have the flow chart ready for haloarenes. How do you read this flow chart? For those who've been following this channel, you just have to copy it, nothing more. But for those who are new to the channel, see over here, I've got benzene or alkyl benzenes, fluorination explosive with reaction with halogen in dark. So we carry out chlorination or bromination by this method. The condition is low temperature, Lewis acid as catalyst. Iodination is a reversible reaction. So we carry it out in the presence of oxidizing agents. Aniline converted into, so of course if you want you can write over here C6H5Cl, C6H5Br. I have clubbed all of these into haloarenes because I believe that by the time you finish watching this video, you would be confident enough to understand which haloarene I am talking about over here. If you notice in this flow chart, here is the name reaction. Here is the Benzene reaction. Interesting, right? If you want, you can add the names of the products over here in brackets as well. So this particular flow chart is very, very useful. So please feel free to copy it, draw it yourself. You can also use different colored sketch pens for these set of two reactions. Don't use too many colors. Too many colors will also be confusing. So for example, if I am talking about halogenation, I could use one set of sketch pens, and for the Sandman reaction, I could use the other set of reactions. So you know what will happen when you sit for your exams, you close your eyes and the colors will speak to you. They will give you the answer. Now, for students of class 11, those who are wondering, why don't I have flowcharts like these for alkanes, alkenes, alkynes? They are very much there on the channel. Feel free to use them. If you want, I can slightly zoom it for you so that you can note down what we've got over here. Right? There we go. And then this is it. So in this particular flow chart, we have covered only the preparation of haloarenes. You can also draw this on an A4 size sheet And when we do the properties, you can do the properties like this. So you will have the preparation and properties all in one place. In fact, I have put the flowcharts for all the compounds on my Google site, Pen and Paper Chemistry. Please feel free to use those flowcharts to your advantage to make your learning easy and fun. See you in the next video soon. Take care.